Recording. Okay. We left off looking at the electrical and chemical driving forces. And so we're going to pick up right there and complete looking at that objective. Again, here is that helpful video that I just mentioned. But we're going to go ahead and just do a quick review on the electrical and chemical. And then we'll look at how we determine the magnitude of the electrical driving force. So who can recall what we said about the electrical driving force? How was that different from the chemical driving force? And let's look at the magnitude of the electrical driving force. So while we know what that force is, there is a gradation, right? We can determine different strengths, different magnitudes. And so we're going to look at here how we can determine how strong or weak that electrical driving force is. So the first thing we want to say here is that the magnitude of the driving force is basically a measurement of the strength of the membrane potential. The strength of the membrane potential. And we said that the membrane potential was represented by V subscript M. And just to sort of summarize what we said last time about the membrane potential, it was based on the unequal distribution of charge, the separation of charge, the fact that there are more anions inside the cell, so there's more of a negative environment inside, and there's more cations outside the cell, so there's more of a positive environment outside. And so what that creates, that unequal distribution, creates a pull, creates a potential, right, for things to want to move in one direction or the other. Now, the strength of that membrane potential is the value that we ascribe. So let's say I tell you that a resting cell is negative 70 millivolts. The inside of the cell is negative 70 with respect to the outside of the cell. And that separation creates a force that wants to pull ions in one direction or the other. So that's the first thing we want to say here, is that it's the strength of the membrane potential, or the VM. The other thing is that the amount and type of charge is going to be dependent, right? It's going to be dependent on the amount and type of charge. Again, on the particle that we're looking at, the particle in question. All right, so to sort of break this down here, this is determined by whether the particle is a cation, which would be a positively charged particle, or an anion, which would be a negatively charged particle. Also included here is the amount of charge, so whether it is a monovalent cation or anion, all right, so whether it's monovalent. And monovalent means one charge, whether that be positive or negative, or divalent, right? Which simply means two charges, again, positive or negative. So the amount, monovalent or divalent, and the type, positive or negative, therefore cation or anion, is the second factor that determines the magnitude of the electrical driving force. All right, so let's look at an illustration here and look at what some different magnitudes look like. All right, so in our first scenario, we've got positive charge on the outside. All right, we know that this is on the outside of the cell. We've got negative charge on the inside. And so if we think about a positively charged ion, a cation like sodium, its direction of movement will be to the inside of the cell, right? It's positively charged. It is a monovalent cation. And so it's going to simply want to move to the inside of the cell. okay? And let's say at this scenario or in this state, the membrane potential equals negative 60 millivolts. All right, so this is sort of our basis to understanding how the magnitude of the electrical driving force can change. So our first scenario, a monovalent cation moving into the inside of the cell, the separation of charge here is negative 60 millivolts. Let's take another cell, another scenario. Let's say we have twice as much positive charge. Oh no, okay, my Zoom kicked me out and I think I lost all of the drawing. So let's go ahead and start again. Technology can be very frustrating. I apologize, guys. Let's get back to our three scenarios. So we've got we said the VM in this first case was negative 60 millivolts. And then we said that we had cations on the outside, abundance of anions on the inside. And so if we look at a single charge cation like sodium, it had a strength wanting to move inside. So this is the electrical driving force wanting to move sodium onto the inside of the cell, okay? And the magnitude of that, really important, is negative 60 millivolt. That's how strong sodium wants to move. If you look at another case here, so now we have twice as much charge on the outside and twice as much on the inside. And again, if you look at a single charge monovalent cation like sodium, it's going to want to get into the cell, but here it's going to really want to get into the cell. And that is simply because we have more of a separation of charge. We have twice as much anions on the inside, twice as much cations on the outside. And so sodium wants to get into the cell with twice the magnitude of the electrical driving force as we saw in this first scenario, okay? So that would look like two arrows, right? Two large arrows indicating it's twice the magnitude. And so can anyone predict what the VM in this case would be? Can anyone predict what the VM, the membrane potential, in the second scenario would be? We have the same cation, right? But now our separation of charge is twice as much. Perfect, yes, so 120, specifically negative 120. Excellent, excellent, thank you. So this would be a VM of negative 120 millivolts. So we can see as the polarity of the cell changes, as there becomes more or less of that positive or negative environment, that influences how strong, right, the magnitude with which the ions, the particle in question, wants to move according to that driving force. So the magnitude of the driving force is influenced by the polarity of the cell and the degree of that polarity, how strong or weak that polarity is. And then the other part is going to be the charge of the particle. So let's look at another scenario here, third one, that would highlight that second factor. So again, we've got positive on the outside, negative on the inside. So very similar to the first scenario here. But now we're looking at a cation that is a divalent cation. So let's look at calcium. Calcium has two positive charges, so it's divalent. What do you think the strength of the membrane potential in this third scenario would be? And what would that value be? Feel free to take a guess. Feel free to take a guess. Again, it doesn't have to be perfect. This is an opportunity to learn. All right, yes, perfect. Thank you. So negative 120 millivolts as well. And so the key here is, although the polarity of the cell is the same as in the first scenario, now we have two charges on our particle. And so that's going to double the magnitude of the electrical driving force. So just like we saw in scenario 2, calcium is going to really want to get into the cell, right? Still trying to get to the negative environment. And the strength with which it wants to do so is going to be twice as much as an ion like sodium because it has twice the charge. So the VM, or the membrane potential in this third scenario, would also be 120 millivolts. All right. Let's pause here and see if we have questions. Okay, what we're trying to illustrate here is what are the things that determines the strength of the electrical driving force? What are the things that determines how much the particles want to move according to this force? And just to summarize, those would be the strength of the membrane potential, all right, which is the polarity, which is the degree of the separation of charge, and the particle in question, the type and amount of charge on the particle in question. All right, let's see. Can there be twice the charge outside the cell and only one charge inside the cell, or vice versa? So this is a good point. And while we theoretically will talk about one negative charge or one positive charge, this is just illustrating the strength of the charge. So there can be more of a positive environment on the outside of the cell, but that is going to be mimicked by an equal distribution of negative environment on the outside of the cell. So when we talk about the polarity of the cell, that is reflected on the outside and the inside, if that makes sense. So if there is a negative 70 millivolts, that means that the inside of the cell is negative 70 with respect to the outside. If that membrane potential goes up to negative 120, the inside of the cell is negative with respect to the outside of the cell. So the membrane potential is always sort of referencing the inside with reference to the outside. So it's always speaking about both the extracellular and intracellular fluid, but then it's going to be looking at the value of the inside in terms of that negative charge, okay? So we're really looking at where is the overwhelming negative or positive charge? Is it more on the inside? Is it more on the outside? And then the number that put on that is the degree of that unequal distribution. All right, really good question there. Any other questions? Okay, good, good. Any other questions here?